So this is the last topic, no, of the under beam, no, in steel design. So beam bearing plates and column base plates. So the design procedure for column base plates is similar to that for the beam bearing plates. In here, now we'll only discuss the beam bearing plates because the design procedure for column base plates is just similar to the beam bearing plates. And the determination of the thickness of the column base plate requires consideration of flexure, so it logically belongs in this chapter. No, if you try to scan the book, no, by Sigui in 2013, after this one, the beam bearing plates is the column base plates. Actually, daghan pa siya topics, no, sa underbeam, but will only like will end in this topic. In both cases, the function of the plate is to distribute a concentrated load to the supporting material. So after the beam, no, so you have the so you have here the beam. No, this is the wide flange beam, and this is the concrete column. To transfer the load, no, there should be a plate, no, transfer the load of the beam to the supporting material or the column. Types of beam bearing plates: one that transmits the beam reaction to support, such as the concrete wall, see figure 5.36. So this one, beam support, that is bridge abutment, no, beam reaction to a support, such as a concrete wall. For example, is a bridge abutment. No, the abutment atong starting support, no, sa bridge. Siya mo na siya ang itawag na abutment. Then one that transmits load to the top flange of the beam. So number one is one that transmits the beam reaction to a support. Now gikan sa load, there is the beam reaction to the support, and the other one is that transmits load to the top flange of a beam. So from the reaction, no, at the support, i-transmit niya sa top flange sa beam, no, from the reactions in here, transmit niya dito sa top flange sa beam. In the design of bearing plates, there are 3 design steps. Number 1, determine dimension, that is L sub B, so that the web yielding and web crippling are prevented. Now, these are the limit states, no, for the design of bearing plate. Number 2, determine dimension B. This L sub B, this is the bearing length, no, and this B, bigger B, this is the like the base, so that the B times L sub B, this is the area of the bearing plate, is sufficient to prevent the supporting material, that is the column, no, or usually the concrete, from being crushed in bearing. So I believe, no, you already learn, no, about bearings sa inyong elementary mechanics of materials. And number 3, determine the thickness T, no, of the bearing plate, so that the plate has sufficient bending strength. So the dimension of L sub B is for yielding and web crippling. Now later on, we'll know no what is this web yielding and web crippling, and also get the value for the B, no, and the thickness to have sufficient bending strength, no. That is these are the steps for the design of the bearing plate. So the ASC chapter J design of connections address the web yielding, web crippling, and concrete bearing strength. Web yielding. So what is this web yielding? This is the compressive crushing of beam web caused by the application of compressive force to the flange directly above or below the web. Uh, so ang critical ani or gitarget aning web yielding is of course so the web, no, because of the compressive force, no, application of compressive force directly above or below the web. So that is if you remember, there is this distance k, this one, kaning k, no, from the outermost fiber of the flange to the fillet. Muna siya ang value sa k. After that, that is the yielding of the web. Diri mo occur ang yielding sa web. This force can be an end reaction from a support, no? Or it could be a load delivered to the top flange by a column or another beam. It could be an end reaction from the support or a load delivered to the top. So as I've discussed ganina, reaction force, i-transfer niya sa top flange of the beam. So kung i-transfer niya, syempre maagian mo ang web, no? That's the time, especially kung ang web nimo is grabe ka nipis. So ang tendency ani is dali ra siya mo yield. Like here, no, this figure, there is this load, no, simply supported beam, no. Then you have this load. The bigger picture of this one is this one. This is counteracted by the reaction. This reaction is transferred, no, to the top flange. Then there is this moagi siya sa web, so mo nang tendency mo yield, no, ang web. After the value of this k, no, this k is this from the outer most part of the flange to the fillet, no, katong bawg sa flange, after sa flange. This is web yielding. Web yielding at support. This is when the load is transmitted through a plate. Web yielding is assumed to take place on the nearest section of width TW, no. So at support, there is like load at support. So the web yielding will occur on the nearest section of width TW. What is the nearest section that is directly below the load, no? In a rolled shape, or the shape that is manufactured or produced using hot rolled, no, shape. Yeah, sa atong I think I don't know, no, sa nakakuha na ba mo? Naka field trip ay wala ay no? Field trip sa yes, naka field trip ta sa kuan itong Steel Asia ba to? So mo to siya ang pag hot rolled, no, pag manufacture sa steel. This section will be at the toe of the fillet. So this section, no, TW, at a distance K from the outside face of the flange. Now, as I discussed kanina, the web is after the K value, no? This TW. A distance K from the outside face of the flange. If the load is assumed to distribute itself at a slope of 1:2.5, the area at the support subject to yielding is this TW thickness times 2.5 K plus LB. LB is this one. This is the plate. Now this the plate. This one. This is the plate. So actually this is the kilid view, no? The side view of the plate. Then kung imo siyang tan-awon diri nga side, that is the length of the B, big B, no? The base, no? Sama na siya. This one is the side view of the beam, then this is the front view of the beam. So kung ato siyang i-drawing, there is actually a plate. There is actually a plate. This is the, sorry for the wrong thickness. I mean, this is the plate. This is actually the B, front view. Then ang kilid ato, no, nga length, that is the L sa B. So the nominal strength, no, for web yielding at the support, according to this equation, AISC J10-3, is this one. The nominal strength is equal to the yield strength times the thickness of the web times 2.5 K. This is the distance now from the outermost flange fiber to the fillet section plus this ELSA B. Note that the bearing length or this ELSA B at the support should not be less than the value of K. K is the distance, this one, this distance. Then web yielding at interior load. At the interior load, the length of the section subject to yielding is this equation, no? So that you can get the value of the bearing length L sub B. Meaning, web yielding at your load, if you have the beam, wala siya sa support, no? Na siya somewhere sa beam, but wala siya sa support. Then, nominal strength is this equation equal to yield strength times the thickness of the web times 5K plus this L sub B. For LRFD, the design strength is the resistance factor times the nominal strength, where the resistance factor is equal to 1.0. And for ASD, the allowable strength is this, diba? This is the basic concept now of for ASD, the allowable strength, where the safety factor is 1.5. So this is for the web yielding, no? For the web yielding. Actually, we have the three limit states, no? We have the web yielding, the web crippling, and the strength, no, of the plate, bearing plate. The next is we'll try to understand the web crippling. Web crippling is buckling of the web caused by the compressive force delivered through the flange. So it's actually like almost the same concept with web crippling, no? The web crippling is like katong ganina is mo yield lang siya, but this web crippling actually is worse, no? If this is the flange, this is the web, mo cripple siya, like cripple, something like that, no? So this is the cripple part, the web crippling. So for interior load, the nominal strength is this equation. It is long equation. This R sub n nominal strength is equal to 0.8. The thickness of the web squared times this quantity 1 plus 3 times the ratio of the length of the bearing over D. D is the depth, no, of the for example, the wide flange, no. For example, the shape is wide flange times the thickness of the web over the flange thickness to the power of 1.5. Then close parenthesis, square root of E modulus of elasticity, yield strength, thickness of the flange over the thickness of the web. For a load at or near support, if the load is at near support, no, kato ganina is for the load, interior load, no, not in the support. But in here, for the load near or at or near support, no greater than half the beam depth from the end. It is no greater than half. Okay, if this is the say this is the column, then you have the beam, no? This is the depth of the beam. Sorry. Batik kayo siya pag-drawing. Then naa kay bearing, no? For example, ano lang. Siyempre, ano lang ito. Let's erase this one. Kaya malag siya mo. So, naa kay column. So, ay! Yeah, forgot. Naman dahil ko'y kuan. Di ako ko'y pagkatuwing. Itong i-erase, no? If this is the column, then naa kay bearing plate. No, ana lagar. So, according to this one, if for a load at or near the support, no greater than half the depth and half of beam depth. So, this is the depth of the beam, for example. No, muna siya ang depth sa beam D. Half of this one, dapat dira ang consider nimo load at or near the support. Half of this one, D over 2, dapat from the end, no, to D over 2, diri lang ang load. Like, nakay load diri. Or if you have load in here, makonsider siya nga for a load at or near the support. So, this is the nominal strength, no? For a load at or near the support, the nominal strength is this equation from the AASC, equation J10-5A and -5B. For this bearing length L sub B over D, depth of the beam or this wide flange, less than or equal to 0.2, this is the nominal strength, equal to 0.4 web thickness squared times 1 plus 3. This ratio, bearing length over D times the width of the thickness of the web over the thickness of the flange to the power of 1.5. Square root of EFY, thickness of the flange over thickness of the web. This is for this condition. Or the length of the bearing length over the depth of the beam or the wide flange is greater than 0.2, then your nominal strength is this equation, no? This long equation. So, magbari siya diri, no? this 4 LB over D minus 0.2. Naa siya, maalis din siya ni Moning 3 times LB, L sub B over D by this one. No? Note that the resistance factor for this limit state, for this limit state for the web crippling is the resistance factor is 0.75 and the safety factor is 2.0. Remember, for the web yielding, the resistance factor is ganina, yes, for LRFD, yes, 1.0 and 1.5 now safety factor. For web yielding, for web crippling, this value. This time, we'll discuss the another limit state, which is the concrete bearing strength. Now, the material used for beam support is usually concrete, which must resist the bearing load applied by the steel plate. The nominal bearing strength specified in the ASCJ8 is the same as that in ACI and may be used if no other building code requirements are in effect. No, we will use the ASCJ8, no, if there is no other building code requirements. So we have here the top view, no, in figure 5.38. This is the the plan. No, this is the support. This one outside, and this is the bearing plate. This rectangle here, and the A sub 2 is the area, the full area of the bearing plate. This is the kung imo siyang tan-awon sa kilid, this is the side view. This is the beam and the bearing plate. No. So A sub 2 is the full area of the support. So if the plate covers the full area of the support, no, the nominal strength is this one, 0.85 times the concrete strength, no, FC prime times the area 1. If kung ang column nimo, for example, the concrete column nimo, full area ang plate. If this is the P of the column, full area, like this is also the area. Sorry. Application. Like if this is your column, no, top view dimension, full area of the support, ing ani pod ang length sa imuhang bearing plate. So this is L sub B over by B, no. So this is your nominal strength. If the plate does not cover the full area of the support, the nominal strength is this equation, no. 0.85 FC prime A1. This is the area of the plate. Square root of area of the support over area of the plate less than or equal to 1.7 FC prime area of the plate, no. Like for example, if this is the column, then naa kay bearing plate, no. Wala siya na-cover sa full area sa support, no, naa kay bearing plate dire. So this is your nominal strength, where the FC prime is the 28-day compressive strength of concrete. A1 is the bearing plate, bearing area, no, bearing area plate, and A sub 2 is the full area of the support. If A sub 2 is not concentric with A sub 1, then A sub 2 should be taken as the largest concentric area that is geometrically symmetrical to similar to A sub 1. See figure 5.38. Yes. For LRFD, design bearing strength, no, design the resistance factor for this limit state, no, the strength, the resistance factor phi is 0.65, and for AESD the safety factor is 2.31. For the plate thickness, because we are after of the plate thickness when we talk about bearing strength, so we are after of the plate thickness, no. Once the length and width of the plate have been determined, the average bearing pressure is treated as uniform load on the bottom of the plate. Like for example, this figure, no, which is assumed to be supported at the top over a central width of 2K and length L sub B. Like for example, this one, this is actually the top view. If you try to look at it at as inside view, this bearing plate is there is the uniform load, no, at the bottom. The average bearing pressure is treated as uniform over the length of the bearing plate, which is equal to 2K times the N, no. This K, actually this is the distance from the, if you remember ganina, we discussed earlier, the outermost flange to the fillet, no. This one, this also equal to this one, 2K plus 2N, the whole length, no, uniform load. The plate is then considered to bend about an axis parallel to the beam span. Thus, the plate is treated as a cantilever span length end. So, the plate, no, there is this cantilever span length n, which is equal to B. This actually the B minus 2K divided by 2, and with L sub B. So this one, yeah, yes, this is actually B, no? The whole length is B, base of the bearing plate, and the into the paper length, this one is L sub B, the bearing length, no? And we consider the 1 inch 1 inch uh, with a uniform load. All right, from this L sub B, we consider the 1 inch, this one. So considering this 1 inch width with a uniform load, the maximum bending moment in the plate is M is equal to R over B times L sub B times N over 2, or Rn squared over 2B L sub B, R where R is the beam reaction, and and R over B, sorry, and R over BL sub B is the average bearing pressure between the plate and the concrete, no, moment. So the beam reaction divided by this area of the bearing plate. So this is the pressure, no, mahimo siya pressure times, so the pressure times N, so mahimo siyang uniform load times the distance, which is N over 2 moment, no, the maximum bending moment. All right, because the critical part here is actually this one, kaning at k distance. I mean, diya siya mo ang iyang critical nga part. So actually this moment is derived, no, you have the reaction R due to the load, no, in the beam. So load sa beam, so naa kay reaction R. So to get the pressure, no, at the bearing plate, so the reaction divided by this area. So actually kani siya is pressure na ni siya. So pressure times n mahimo siyang uniform load in kilonewton per meter times the distance n over 2. Then considering the 1 meter length, no, 1 inch width, no, considering 1 inch width, so mo na siyang, or if we like the unit is English unit, so na 1 inch width, then the moment is this one, r n squared over 2bl sa b. For a rectangular cross section bent about a minor axis, the nominal moment m sub n is equal to the plastic moment m sub p capacity, as illustrated in figure 5.4. For a rectangular cross section of unit width and depth t, the plastic moment is this one. Yes. Actually, considering also considering the 1 inch length, no, kaya mo na siyang ipadako, kani siya dapit. This will look like this one, no? This is 1 inch and a thickness t, no? So, on and bent, no, about the minor axis, so you'll have the moment. If you try to moment at this part, no, so the Fy times the distance now of the uniform load, that is thickness divided by 2, and times 1 inch, and times again the distance at the centroid of the force, no, of this uniform load, that is t over 2. So mo nang the moment, no, plastic moment is equal to yield strength times t squared over 4. For LRFD, since the design strength must at least equal to the factored load moment, so from this one, the plastic moment, this actually at the design side, no, substitute this one in here. This is the concept of design, that the design strength must be greater than or equal to the factored load moment, or M sub U. Factored load moment, or due to the factor, due to the loads, or load combination, no? Then this the resistance factor, no, for the strength, no, the for bearing strength, for bearing plate, no, resistance factor for bearing, actually this is for bearing, is 0.9 times the value times the plastic moment, which is equal to Fy t squared over 4, greater than or equal to the ultimate load factor times n, katong ganina, no, this one, due to due to the loads, applied loads, no? So, ultimate load times N over 2B times L sub B. Or, manipulating this one, this will become T is equal to greater than or equal to square root of, no? Uh, from this equation, we have 2RU, this one. Or, 2 divided by 0.9 T, that is 2.22. This one, no? Where the R sub U, this is the factored load beam reaction due to the applied loads. This is for LRFD, and for ASD, the allowable flexural strength. Yes, this is the same actually with this one, no? Since it's ASD, so using the safety factor equal to 1.67 for bearing plate, no? The plastic moment divided by the safety factor is greater than or equal to the applied moment. So the equation, no, of that we get for the plastic moment is this one. Substitute this one to this M sub P over the safety factor. Then the moment, applied moment, is just this R sub A. This is the applied service load beam reaction times N squared. Katong ganina, no? Kani. Substitute this one to the right side, this M sub A. So the thickness will become this value for ASD, no? Where R sub A is the service load beam reaction. Then we'll try to discuss the example.